Good morning. My name is Michael Ibrahim, and in this presentation, I'm going to explain my developed system for the CityLearn 2022 challenge. First, I'm going to introduce the overall architecture of the system. Then, I'm going to describe the implementation of the predictors for the energy consumption and generations, and the predictor for carbon emission. Finally, I'm going to describe the model predictive control system used. The developed system works as follows. The MPC uses the design parameters 24 steps ahead predictions of the produced and consumed energy and carbon intensity. Also, it uses the current battery storage and the produced and consumed energy at the current step by the building, and the MPC produces a charge or discharge decision for the building. Also, in this system, the produced and consumed energy predictors are time variant, so they use the current observation of the produced and consumed energy to update their parameters. For the energy generation prediction, first I trained a linear regression model to estimate the generated energy at building J based on the observations of the generated energy for the given 5 buildings. The parameters alpha 1 to alpha 5 are updated every 168 steps of the simulation based on the actual generated energy at building J. This kind of model is motivated by the high correlation between the generated energy of the buildings. As you can see, the correlation between building 1 and building 5 is 0.98, and the correlation between the generated energy in buildings 2, 3, and 4 is almost 1. Then I trained a second linear regression model to estimate the generated energy at building J based on its historical observation, where the matrix sigma is calculated offline based on the historical generated energy for the given 5 buildings. Then, during the simulation, the generated energy at building J is estimated based on a linear regression meta-learner. The parameters of the meta-learners, beta 1 and beta 2, are updated every 168 steps of the simulation based on the actual generated power at building J. Finally, I train my forecast based on a minimum and a maximum estimate calculated at each step based on the generated energy of the given 5 buildings. As a final note about this estimator, numerical experiment shows that this estimator is very accurate. For the energy consumption, first I trained a linear regression model to estimate the consumed energy at building J based on the observation of the consumed energy for the given 5 buildings. The parameters alpha 1 to alpha 5 are updated every 168 steps of the simulation based on the actual consumed energy at building J. Then, I trained a linear regression model to estimate the consumed energy at building J based on its historical observations, where the matrix sigma is calculated offline based on the historical consumed energy of the given 5 buildings. Finally, during the simulation, the consumed energy at building J is estimated based on a linear regression meta-learner. The meta-learner parameters, beta 1 and beta 2, are updated every 168 steps of the simulation based on the actual consumed power at building J. Numerical experiments show that the root mean square error of the estimated consumed energy after 24 steps is almost the double of the root mean square error of the estimated consumed energy after a single step. For the carbon emission predictions, I have trained a nearest neighbor regression model based on the carbon emission file given in phase 1 of the competition. This model produces perfect predictions since the file used in the training of the model was used during the final simulation. Now let's introduce the model predictive control parameters. C hat I, the difference between the estimated produced and generated electricity. Pi, the price of the electricity at step I. II, the carbon intensity at step I. P hat no, the total price of the electricity for the next 24 steps if there is no battery, and it's calculated using C hat I and Pi. I hat no, the total carbon intensity for the next 24 steps if there is no battery, and it's calculated using C hat I and II. R hat no, the total ramp for the next 24 steps if there is no battery, and it is calculated using C hat I. M had the maximum net electricity consumption during the previous 730 steps. L had the load change weight, and it is equal 1 over M hat multiplied by 1 minus the load factor if there is no battery, and it is calculated using the observation from the previous 730 steps. In the beginning of the simulation, M hat and L hat were initialized using the average of the historical values of the net consumption of the given 5 buildings. The model predictive control uses the following variables: xi, the decision at step I; si, the battery storage at step I; n plus I and n minus I, which are the positive and negative parts of the net energy consumption at step I; ri, the ramp variable at step I; L, the slack between the maximum net consumption M hat and the current positive part of the net consumption N plus I. The model predictive control can be described by the following objective and constraints, and after solving this linear program, the decision x0 was used as an action for the building. The first part of the objective is the total price of the purchased electricity normalized by the total price of the electricity when there is no battery. The second part of the objective is the total carbon emission normalized by the total carbon emission when there is no battery. The third part of the objective is the total ramp normalized by the total ramp when there is no battery. The fourth part of the objective is maximizing the load factor, and this can be achieved by maximizing the average net electricity consumption, or in other terms, minimizing the negative part of the net consumption, and by minimizing the maximum net consumption, or in other terms, minimizing the slack L between the maximum net consumption M hat and the positive part of the net consumption N plus I. Finally, I noticed that the error in C hat I after 24 steps is almost the double of the error in C hat I after a single step. So I use this factor in the objective to reduce the effect of the error in the late estimates. The first set of constraints are the electricity conservation constraints. The first constraint means that the net electricity equals the storage decision at the previous step plus the consumed energy minus the produced energy. The second constraint means that the battery at step I plus 1 equals the battery at step I plus the storage decision at step I. We can note that S0 is the current battery storage of the building. The second set of constraints are the ramp constraints, and they mean that the ramp at step I equals the absolute value of the difference of the net electricity consumption at step I and the net electricity consumption at step I minus 1. Also, we can note that N plus 0 and N minus 0 are the current positive and negative net consumption parts of the building. The third set of constraints are the slack constraints. The final set of constraints are the bound constraints. We can see that the decision variable x of I is between -1 and 1, and the battery storage Si is between 0 and 1, and the remaining variables are non-negative. Thank you.